When we look at it, when ARM look at it, we don't just look at it as, okay, the power performance area thing in the car in a processor. That, yes, we look at that, but it's not the only thing. We look at the full cloud to car picture. We look at, for an OEM, how do we ensure that full picture is optimized?
ARM is the industry's highest performing and most power efficient compute platform with unmatched scale that touches 100% of the connected global population. Together with the world's largest computing ecosystem and 22 million software developers, ARM is building the future of AI.
Hi, my name is Junko Yoshida. I'm the host of Junko's Talk to Us, and we have been doing this domain-specific AI video podcast series. We started out this conversation with AI-driven applications, and we moved our conversation to AI-defined vehicle. I think that's the terminology used. And then you brought in SOAFEE, which is what the industry knows as software-defined vehicle. So I want you to summarize how all these things are connected before we move on to the next topic.
Perfect. Sure. I'll actually do it in the reverse order.
Okay. All right.
Not to confuse your listeners, but just to basically give me a little bit better clarity. So, see, fundamentally, as we talked about software-defined vehicles, let's start there, right? So what? It was like, what, 3-4 years ago we started in the industry, and we all started talking about software-defined vehicles. And the idea for software-defined vehicles started off saying we need to establish this whole infrastructure where even after the car rolls out of dealership, it needs to be upgradable. The experience needs to be upgradable. There needs to be new use cases, new software applications that can be enabled, right? So that was the essence. So obviously, what does it actually mean is we need to build that infrastructure, the cloud to car infrastructure. And we can talk about cloud to car and what ARM is doing there in more detail, in the next section. But that's where things like SOAFEE come in. The essence of SOAFEE was fundamentally to go, like I said, simplify, standardize the pieces of non-differentiating software and enable that infrastructure from cloud to car and drive that, right? And then moving on to the AI-defined vehicles, right? And this is something that we've been talking about in the last couple of months is AI-defined vehicles really is in that application domain, right? Because when we talk about AI-defined vehicles, is something that sits on the SDV infrastructure. It's not replacing SDV, it uses SDV, right? So when we talk about AI-defined, it talks about all of these use cases that AI is unlocking, like the cockpit applications that I talked to you about, be it end-to-end AI, be it other aspects. So AI-defined vehicle is how AI is changing the user experience and applications in the car. That's what AI-defined vehicle is. But then you need the infrastructure of this whole cloud to car standardization, cloud to car SDV infrastructure that enables this, right? So that's how it is. So it's like the SDV, the SOAFEE angle, all of that stuff solves the infrastructure and solves all of the foundational elements. And then you have AI-defined vehicle that basically primarily latches onto the new AI application that can be unlocked, primarily driven by LLM changes, generative AI developments, and all of that stuff. Does that make sense?
Yes, thanks.
What role does the cloud play in this, other than just being a source of software updates? Is it actually going to be working interactively with the local AI?
Absolutely, Ron. I think I'm just thinking, where do I begin? Because as I mentioned, so today, if you look at all of the learning that happens, be it even in end-to-end AI, by the way, if you listen to the podcast that Silvius, who is the head of software at Wave, and I did, he actually corrected me at one point, saying the learning still happens in the cloud. I misspoke in that podcast for a second at saying there is some amount of learning happens in the car, but I said no, even in that sort of a model, learning still happens in the cloud, right? So inference happens in the car. Now the model gets updated based on the learning information constantly, right? So cloud basically, is absolutely going to be critical piece of this entire thing, right? Because as the models learned and improved and developed in the cloud, new applications get developed in the cloud because cloud has this access to all of this data, right? Going back to the example that we were talking about earlier, mapping data, right? So your car is somewhere running a model, right? You get a feed based on mapping information, real-time mapping information and traffic information or weather information or whatever. All that data is actually in the cloud, right? Because some weather service provider would have actually updated something. Some traffic service provider would have updated some data onto the cloud, right? So all of that information is really in the cloud where you sort of have that, have that interaction. So be it dynamic applications like that I mentioned, or backend learning, cloud is always in the game. Now, it's super, super critical, Ron, to ensure that your compute architectures between the cloud and the car remains as similar, as same as possible, right? Why? When applications get developed in the cloud, if it's both the ISA, the instruction set architecture, x86 or ARM, for example, and if the AI device and AI architecture, if it's different, then imagine when it has to get ported over onto the car, then it has to be recompiled because it's written for a different architecture. Then you got to get recompiled. You need to basically re-optimize it, right? Because the acceleration options that you have in the cloud on a different architecture may not be in the car platform that you'll be deploying it. So again, that's why we talk about ARM talks about ISA parity. ARM in the cloud now, we can very proudly say, right, that we have a very, very good presence in the cloud, the ARM architecture, right, thanks to our partners who are actually building cloud processors and data center processors using ARM architecture. So there's very good a mix of ARM architecture in the cloud from an ISA perspective. And in the car, it's predominantly ARM when it comes to the central compute architectures, right? So you have that ISA parity between cloud to car, and that's that's key, that's essential, right? And then the second thing is the AI architecture, right? So if you think about, if you have the same AI infrastructure in the car, be it GPU or accelerator based, and then you have the same architecture in the car as well, then you have parity there, right? You can actually not just compiling and recompiling problem, you can also use same tools and flows. You can then basically optimize the same thing. I mean, how many times, Ron, in your career or in my career, we've looked at a problem, we've used an entirely different tools and flows, and we don't get the same result, right? We basically get entirely different picture. So hence, the cloud will be important. The parity between the cloud and car is going to be even more important. And that's what I talk about, the infrastructure, right? And how do you sort of enable that cloud to car infrastructure and make it as robust as possible, so software development in the car, so in the cloud that gets deployed onto the car is as seamless as possible.
Does that eventually get us to the point where, for instance, a single end-to-end model could be distributed between the car and the cloud?
Basically, okay, there's always this thing about how much compute can be supported in the car, okay? Obviously, you can't have gigantic servers in the car running, right? So I mean, again, from a development perspective, people started there, but that's not efficient from a cost perspective, right? So there's always going to be sort of optimization that needs to happen. So the model can be same, but I think the way some of our partners basically are doing is you sort of distill it down and then say, okay, here is how this inference model is going to run. But again, it depends on availability of compute infrastructure in the car, and then how we can actually optimize for it.
Can I ask a question? Since we were talking about cloud to car, is that to do the end-to-end properly for highly automated vehicles, is cloud really the essential component to enable that?
Yes, absolutely. Absolutely important, right? Because like I said, most of this model training, model optimization, and development of new applications happens in the cloud, right? You don't do it on the car platform. It gets deployed onto the car, right? But development happens in the cloud, and optimizations happens in the cloud. So it is definitely a very much integral part of the full story. And that's why, again, Junko, one other thing, when we look at it, when ARM look at it, we don't just look at it as, okay, the power performance area thing in the car in a processor. That, yes, we look at that, but it's not the only thing. We look at the full cloud to car picture. We look at, for an OEM, how do we ensure that full picture is optimized, starting from software development part, using virtual platforms and stuff, how early they can actually do it in the cloud. Again, when I say virtual platforms that we enable, that gets installed in the cloud instances, right? So we then sort of do application development in the cloud based on those virtual platforms, all the way from what needs to be done in the cloud for software development to what needs to get deployed onto the car in a power, performance, and area efficient manner is what we are actually focusing on. So it's not just, okay, we're going to basically have this particular IP and there is some other alternative with a better PPA story, it's going to win. But yes, yes, maybe that's part of the story. But if you look at the holistic thing, OEMs worry about bigger problems, software stacks. How is this going to be enabled in the cloud infrastructure? How is this going to be deployed onto the car, and so on and so forth? So cloud is absolutely an essential part of the whole equation.
But at this point in time, other than Tesla, I don't see a whole lot of traditional OEMs leverage this cloud to car end-to-end kind of automotive applications yet. What do you think?
I think we're getting there, Junko. I think
Yeah.
we're getting there because the thing that there's a couple of things that are happening, Junko. There, one is some of the traditional OEMs are also catching up in terms of the compute architecture in the car, right? Again,
Right.
it's just multi-dimensional. That's why it's like so wonderful to be in automotive, right? Because it's just, it's chaotic, but it's leaps and bounds improvement in technology, right? So what the traditional, OEMs are also trying to look at is how do we consolidate the system architecture in the car from, again, they have so much legacy of compute architecture in the car, from hundreds of ECUs to tens of ECUs to single digit ECU, single central car compute platform, right? And then so they got to basically sort of ensure that, okay, they consolidate without breaking, any compatibility that they had in the past, or there needs to be some sort of a clean break in terms of how they do it, right? Now, again, some of the newer OEMs, for them, they didn't have to deal with that
Right.
legacy architecture.
They don't have
right?
legacy. Yeah.
They don't have legacy. So for them, it's more like, okay, here's what we're going to do. This is basically, this is the cloud to car infrastructure, and making it sound simple. It's not simple, but that's how it is, right? Whereas for traditional OEMs, there is also this another part of the problems that they're trying to solve. That's why I told you can see some evidence of other OEMs also happening, but again, it's a question of time. It's not if this is going to happen. It's just when this is going to happen for all the OEMs, and when they will be able to sort of say, okay, here's our full-fledged end-to-end story.
Do you have any opinions as for the traditional modular AI applications for the autonomous vehicle versus end-to-end AI-based autonomous vehicle? Do you have any opinions in terms of safety concerns? Because end-to-end, it's pretty much everything is black box, and I worry about that. What's your opinion on this?
If you ask me, my opinion, I am an optimist. I definitely think that there's always this learning curve in the technology, and we will, things will be solved. Things can be solved, things will be solved, right? Now, yes, the end-to-end AI definitely brings a lot of optimization on how things are actually sort of done, right? In terms of the code complexity, in terms of, code dependencies and all of that stuff, right? But at the same time, it's a completely new concept, right? Now, is that going to just replace the whole traditional modular AI, sensor fusion, perception, path planning based algorithm or AI? I don't think so. That's going to happen overnight, right? Because obviously today, most of our partners who are actually developing this has millions of miles of optimization done based on this sort of a traditional modular model, and you can't just check it out, right? Because it's you have to build on top of that, right? It's really, really fascinating technology, and I believe like I said, the compute requirements for that are slightly different than compute requirements on the traditional modular AI model, and how you can slice and dice the compute requirement, and how you can sort of run different aspects of that modularity is different. But end of the day, I think it's definitely sort of something that we are seeing picking pace, and we work with all of them. We work with everybody. So it's just making sure that we get enough learnings. Our thinking is, okay, this is a new way to do it. Okay, we didn't think about it. What do we
Yeah.
have to do that our technology is actually sort of on par to go meet what they are trying to do, right? So
Do you think there'll be a tendency for the electric vehicle manufacturers to get to end-to-end more quickly because they don't have the backward compatibility issues that the traditional manufacturers have?
that's an interesting. I had not thought about this actually, Ron. You're saying the electric vehicle platforms do not have legacy, so maybe the platform architecture, the electronics chassis of that car is don't have any legacy baggage, and maybe they will be able to deploy the end-to-end model sooner.
And they don't have 30 wiring cables to deal with,
Have
things
31.
like that.
I haven't thought about it that way, to be honest. I think it's again, it also depends upon the how much compute power you can actually put in an EV.
Especially in EV. I mean, you're gonna sacrificing your miles, right? I mean, if you
Uh-huh.
have to use a lot of power. Yeah.
Yeah, I mean, definitely not big servers, right? I mean, it needs to be much more cost and power optimized. But yeah, it's an interesting angle. I'll think about it.
I think one of the other people we've spoken with said that the ideal situation for an AI software developer is to have the hardware sitting right on top of 1,000 pounds of batteries.
Right. Exactly. Exactly. I mean, honestly, I'll tell you, some of these, when we go talk to some of these software developers, and it's like, oh, we need more compute. I mean, it's so classic, right? You have the architects and developers and of those algorithms. Oh, we need more compute. The more, the better. Oh, how much is your next generation CPU supporting? Oh, what's the single thread performance? Can we add? Okay, can we get more of that, right? And then it's like, okay, now this is too complex for us to go deploy. So we will have to now think about how do we actually, it's a trade-off all the time, right? But it's nice.
I think that would be good segue to the thing that Suraj, I read your latest blog on ARM's website. You asked in the very beginning of the blog, said, it would be crazy if you think that I know what the workload is for the next generation automotive is, right? And I totally agree. But at the
Exactly.
same time, hardware designers need to know what the workload is going to be. And
Yes.
how do you fill in that gap? I mean,
Right.
what's your suggestion to your potential partners?
Cool. Great question. I think this is where we talk about virtual platforms, okay? Like to fill in the gap, to help us sort of do the hardware software co-development together, okay? So let me give you an example. Let me give you a piece of learning that we actually had. So ARM has been supplying automotive enhanced IPs to the ecosystem, to the industry since 2018. 2018, although we were supplying IPs to the automotive space for the last 25, 30 years, right? But we started launching something called as AE IPs, automotive enhanced, with all of the safety, security, real-time features in 2018. Okay, that was the first generation. 2021 was our second generation, and 24 was our third generation. And we did, releases between those timelines, but these were like big launches where we completely refresh our CPUs and other IPs. So now when we launched our 2021 IP in beginning of 2021, Junko, the hardware platform that became available for the software developers was in early 2023. Okay, because we released the IPs in beginning of 21, and then the silicon partners took about an year or 18 months to go develop silicon, and then about 3 to 4 months of silicon validation when the chip came back from the fab, and then the development boards were actually made available sometime in early 23. So literally 2 years after we had the IP up on shelf to when the software developers got their hands on starting to build software. Okay. That's a significant delay. So in a traditional timeline, Junko, it's probably okay because the vehicle doesn't, as I told earlier, the vehicle from IP release to when the vehicle comes, it's like 5 years, and then okay, it was all okay. But in today's world, when things are changing so rapidly, you can't expect that 2 years of delay when we release the IP. So what we did is, okay, and this was 2021 generation, right? We said, okay, for 2024, we're not going to allow that to happen, okay? So we started working about 6 to 8 months before our IP release with some key EDA partners, who's mentioned in the blog that I wrote. And we worked with the EDA partners to ensure that there are virtual models of our IP available for software development in the cloud on the day of our IP launch. So on March 13th, 2024, when we launched our IP, we actually had virtual models for our IP in the cloud on day one, okay? Not just that. In 2021, we didn't have SOAFEE. We launched SOAFEE in September 2021, okay? So in 2024, we had SOAFEE. So what did we do? Not just the virtual platforms, we actually had the SOAFEE standardization layer enabled on those virtual platforms. So when the EDA partners and our cloud service provider, AWS is our partner, was our partner there, and even now is a very good partner, when they enabled the solution in the cloud, it came in with that SOAFEE framework, right? And then so it sort of had all of that standardization that we've been pushing in SOAFEE. Not just that, because we did that, the SOAFEE partners who've been sort of working on the standardized firmware that we released were able to enable their middlewares on top of it and applications on top of it. So Junko, what essentially happened March 13, 2024, and coming weeks after that was we actually had software development happening at the time of IP availability from ARM. Then our silicon partners started developing chips based on our IPs, right? And then the software partners were basically developing software with the virtual models in the cloud, right? And then, okay, if somebody basically said, oh, for this particular application, in fact, I think we need to make use of 16 cores instead of 12 cores. That feedback was actually passed on to the silicon partner, again, them working together. And then it was like, okay, all right, so this is how real-time software hardware code design was actually enabled. That kind of strategy needs to come in, right? There's no way, like I said, you can't predict what's going to happen 18 months down the lane. But if you actually come up with ways where you can sort of bridge the gap and then enable technologies, that's going to be useful. I think it's foundational to this entire SDV story that we are pushing, because that the industry is working on, because that enables that cloud. You enable the virtual models of the car platform in the cloud and enable that software development on a platform that will eventually go on the same, the car, right? So that's why, those are the things that are absolutely essential. And now, Junko, what we are doing is we just launched, as I said, the Compute Subsystem in June. And now we are basically going to have virtual models of the entire Compute Subsystem in the cloud, right? Not just the IPs that we made available in 2024, but now the Compute Subsystem comes with the virtual models. So it's just even better.
Given the importance of bandwidth and latency between compute modules, is it essential to have the whole platform model, not just the IP models?
It would be really, really beneficial on how much richer you can actually make that model, right? It can start with IP. And that's why, if you think about last year, we were not having a compute subsystem. So now we have the compute subsystem. So it's a much more richer model, right? What does our Xena compute subsystem have? It basically has the CPU cluster. It's got the safety island. It's got, it's got the debug blocks. It's got all of these, core elements. Now, for a software developer, going back to the mixed criticality part, for a software developer, he basically, if he only had the IP models, then he would say, okay, I'm just going to run this application, part of this application that runs on the CPUs, I'm going to run it on the CPU. But I need a separate model for a safety island, right? Now, when the compute subsystem comes in with all of that, he's like, okay, now I have a full model. I'm going to run the safety critical application on the safety island part of the model. And then I'm basically going to run the application on the application core side. So, and then next stage, if you have virtual models for the entire SoC, and then you basically have virtual models for the platform and the ECU, which again, there are, some of the partners are already working on vehicle models, digital twin of the vehicle model, digital twin of the ECUs and all of that stuff. We are talking about it, the reason we are enabling this foundational elements, be it IP or compute subsystem, Ron and Junko, is then partners can scale from there, depending on their SoC implementation. They can say, okay, I'm going to take this, and that's why it's super essential to provide tools like virtual platforms at the core fundamental level, because you can then multiply that depending on what you need. But then if you basically start have a SOC virtual model in the cloud, it's a rigid model, right? It's basically, okay, it just comes with what it has. And the other part of your question was bandwidth and performance requirements. So, some of our, EDA partners, you've heard us talk about it. Siemens, for example, has this technology where they talk about you have the RTL model and you have the software development model going hand in hand. So when a SOC developer is doing performance assessment, at the same time there is a software developer doing software assessment, then you have that one. Both Synopsys and Cadence also have something similar as well. So you have the EDA partners thinking about how do we enable SOC development from a performance and bandwidth perspective, and enable the application development simultaneously. So again, this is we are very, very thankful for all the EDA partnerships that we've actually established, and how do we sort of make use of that at the foundation level for the rest of the ecosystem.
All right. Very good. This, we could have another hour. This was really informative. This is very educational. It sort of illustrates how the fundamental way to not just design silicon, but design the vehicle is changing, and you are in the thickest of it, right?
Absolutely. Yeah. Thank you, Junko. I think and Ron, sorry, some of my answers were very long, but I hope it was useful.
Very good. We'll talk to you soon then. All right.
Thank you.
Thanks.
Thanks, Ron.
ARM is the industry's highest performing and most power efficient compute platform with unmatched scale that touches 100% of the connected global population. Together with the world's largest computing ecosystem and 22 million software developers, ARM is building the future of AI.